I'm Professor Meri Cvetkovska. I'm coming from the Faculty of Civil Engineering, University of Civil and Methodius in Skopje, Macedonia. And the subject of this presentation will be fire safety engineering from theory to practice. The idea for this presentation is to show how we may use advanced calculation methods for defining the fire resistance of elements, part of structures, or all structures.
In the past, the design of structures was made with respect to self-weight, imposed loads, wind, snow, and in seismic regions the seismic action. Fire as an action on structure was not considered. As a consequence of many fire incidents, where parts of whole buildings collapsed, the engineer's way of thinking and sense of logic was changed. Treating fire only through architectural and urban design recommendations and fire protection elements with isolation materials was not enough. There was a necessity for understanding the behavior of construction materials, structural elements, assemblies, and whole structures under fire exposure. According to the Construction Products Regulation 305 from 2011, the structures have to fulfill not only the basic requirements regarding the bearing capacity, stability, and serviceability, but also the requirements considering the fire safety of structures. Other requirements are hygiene, health and environment, safety and sustainability in use, protection against noise, energy economy and heat retention, and sustainable use of structural resources. According to the fire safety requirements, the construction works must be designed and built in such a way that in the event of outbreak of fire, the load-bearing capacity of the construction can be assumed for a specific period of time. The generation and spread of fire and smoke within the construction works are limited. The spread of fire to near the construction works is limited. Occupants can leave the construction works or be secured by other means, and the safety of rescue teams is taken under consideration. Achievement of all these requirements is possible by active fire protection measures, by using alarm systems, sprinklers, installations for distinguishing the fire, etc. By passive fire protection measures, that means by using appropriate structural systems, appropriate materials, etc., and by risk management in case of fire. Different countries have different national regulations for structural design. In order to harmonize these design rules and procedures in the unique regulation, an important step is made with the Eurocodes. The Eurocodes cover only the passive fire protection measures. Fire resistance of an element, of a part, of a whole structure is ability to fulfill the requirements for a specified load level, for a specified fire exposure, and for a specified period of time. According to the European standards or Eurocodes, there are three criteria given to define the fire resistance of structures or structural elements. These are load-bearing function, integrity, and isolation. The criterion load-bearing function expresses the ability of the structure or the member to sustain specified actions during the relevant fire according to different criteria. The criterion integrity expresses the ability of the separation element of the building construction when exposed to fire on one side to prevent the passage of flames and hot gases through it and to prevent the occurrence of flames on the unexposed side. And the criterion isolation expresses the ability of the separating element of the building construction when exposed to fire on one side to restrict the temperature rise of the unexposed phase below specified levels. Criterion E may be assumed to be satisfied where the average temperature rise over the whole non-exposed surface is limited to 140 kelvins or Celsius, and the maximum temperature rise at any point of that surface does not exceed 180 degrees Celsius or Kelvins. Not always all these three criteria have to be fulfilled. It depends on the type of the element. For example, earth walls and slabs have to fulfill all three criteria, but beams and columns only the criteria for load-bearing function. As a first step in defining the fulfillment of the required criteria is to define the temperature rise in the fire compartment with time. There are two options: to use standard fire curve or natural fire curve based on certain data as dimensions of the compartment, the dimensions and the position of the windows, caloric values of all items in the compartment, and so on. The natural fire consists of three phases. Pre-flashover phase includes the ignition, flame spread, heat release, smoke release, and is important for the material reaction to fire. When all items in the fire compartment are affected by fire, the flashover starts, and this phase is followed by the cooling phase. These two phases are important for the fire resistance analysis. For simplification of the analysis, the ISO standard curve was evolved, and it starts at the moment of flashover and only has a scanning branch. Comparison between several real fires and the standard fire curve is presented on this slide. The oldest procedure for defining the fire resistance of structural elements is conducting a standard fire test in specially constructed furnaces. Such furnaces are constructed for testing walls, beams, slabs and columns, and in the last decades even for testing small houses. The behavior of a member as well of entire structure in case of fire depends on many factors as the fire exposure. It means that intensity and duration of the fire action is known. The position of the elements in relation to the fire compartment, it means the fire scenario. The structural system and support conditions, the description and intensity of the external loads, the size and shape of the elements, as well as the temperature dependence of the thermal and mechanical characteristics of the constitutive materials. Consequently, the standard fire test has disadvantages, as do not reliably predict behavior because actual fires and structural restraints cannot be adequately simulated, provide information on local behavior of the elements, but the question about the global behavior of the structure as a whole remains open, and testing programs for investigating the response of a large variety of structural elements under different restraints, different loadings, and fire conditions are impractical and expensive. Besides all these disadvantages, it is still necessary for determining the mechanical properties of the materials at high temperature and checking the adequacy of the developed computational methods. The other, more practical option for defining the fire resistance of structural elements is by using calculation methods, and there are two options: simplified or numerical methods. Both options are offered in all Eurocode treats different materials. Nowadays, in practice, only single structural elements are analyzed by using simplified calculation methods, while worldwide, the global structural response of buildings in fire conditions is accurately determined with proper use of advanced calculation methods. In order to present the fire as a process and the behavior of fire-exposed structures to be more accurate, different softwares were developed, mostly based on the finite element method. These programs successfully incorporate the law of thermodynamics, fluid mechanics, stress-strain analysis, etc. For different fire scenarios, as step 1 for defined element, part of the structure, or whole structure, as step 2, the heat transfer analysis has to be conducted as step 3, and the temperature distribution in the cross-section of the fire-exposed elements to be defined. This step is referred to as thermal analysis. Finally, as step 4, the response of the structure due to static and thermal loading has to be defined, and it is referred to as stress-strain analysis. Nowadays, in practice, only single structural elements are analyzed by using simplified calculation methods, while worldwide the global structural response of buildings in fire conditions is accurately determined with proper use of advanced calculation methods. To demonstrate the results of a numerical procedure conducted with the program file developed at the Faculty of Civil Engineering in Skopje, a case study on fire resistance of centrically loaded reinforced concrete columns is presented. The columns are structural elements that have an important role in preventing loss of global stability of structure under fire. If these elements do not suffer failure, damages shall be of a local character, which will enable evacuation and efficient distinguishing of fire. The fire resistance of centrically loaded reinforced concrete columns depends on shape and dimensions of the cross-section, concrete cover thickness, type of aggregate, steel ratio, intensity of the axial force, as well as the fire scenario, but the dominant effects have the shape and the dimensions of the cross-section and the intensity of the axial force. The set of columns with height 3 meters, with same cross-sectional area of 900 square centimeters, same percentage of reinforcement of 1%, and different column side ratios as 30/30, 25/36, 20/45, and 60/15 as reinforced concrete wall were analyzed. The columns were exposed to ISO-standard fire from all sides and all over the height. All columns were fixed at the bottom side and pin-ended on the outer side, and such support conditions were chosen to enable free expansion in longitudinal direction. As a result of the column's height and the dimensions of the cross-sections, small slenderness ratio was achieved. In such case, the support conditions have negligible effect on the fire resistance, so they were not analyzed. Siliceous aggregate concrete was used, and the compressive strength at ambient temperature was 30 megapascals. The yield strength of reinforcement bars at ambient temperature was taken to be 400 megapascals. In order to define the influence of the lower level on the fire resistance of the columns, the intensity of the axial compressive force was varied. The lower coefficient alpha was defined as ratio between the applied axial force and the ultimate axial force of the column and ambient temperature. The lower coefficient alpha was varied between 0.1 and 0.5. Numerically achieved results for the temperature distribution in the cross-sections of the columns for 3 characteristic moments are presented on the following slides. These are for the columns with dimensions 30/30 centimeters. These are for dimensions of column 45/20 centimeters. And finally, for the column that looks like a reinforced concrete wall. By comparison of the isotherms in the cross-section, it could be found out that in case when the ratio between the two sides of the cross-section is higher, for example 50/60 centimeters, the temperature penetrates deeper in a shorter time period, and the average temperature of the cross-section is higher than in case when the ratio is less or equal to 1, as in case when we have column with dimensions 30/30 centimeters. This results with higher reduction of the material properties and reduction of the bearing capacity of the column. Consequently, the column has lower fire resistance. As part of the analysis, besides the shape and the dimensions of the cross sections of the fire-exposed columns, the intensity of the axial force was varied too. The load coefficient alpha was involved as ratio between the applied axial force and the ultimate axial force of the column. The load coefficient alpha was varied between 0.1 and 0.5. This enabled comparison of the fire resistance of the analyzed set of columns with different shapes and size for different load levels. Numerical achieved results for the stresses in the concrete part of the cross section of the analyzed columns for different coefficients alpha and for different characteristic moments are presented on the next slide. At first moments of fire exposure, in this case half an hour, because of a high temperature difference between the surface layers and inner layers, and because free thermal expansion is not allowed, the concrete core cracks. After a time, high temperature differences is less because temperature penetrates deeper in the cross section and mechanical properties of steel and concrete are reduced and the effect of the axial force becomes dominant, so cracks are closed. This effect happens when load coefficient is less than 0.3 and is not so much expressed when the ratio between the two sides of the cross section is higher. In case of column with dimensions 50 or 60 centimeters, the effect of cracked core doesn't appear for load coefficient higher than 0.2. In case when the load coefficient alpha has higher value, for example 0.35, as a result of the compression stresses caused by axial force and by the restrained thermal expansion, and as a result of reduced mechanical characteristics of the constitutive materials, concrete in the corners of the cross-section is crushed, and soon after this moment, the failure occurs. This photo of column damage in real fire confirms these results. For the analyzed set of columns, the fire resistance curves are a function of the shape of the cross-section and the intensity of the axial compressive force were constructed, and these curves indicated that the highest fire resistance achieves the column with lowest ratio between the two sides of the cross-section. The reason for that is the lowest average temperature of the column's cross-section. The total axial dilatation of the column as a result of the total thermal expansion and the negative axial dilatation caused by the compressive axial force for all four reinforced concrete columns exposed to fire from all four sides and for the load coefficient 0.35 are presented on this slide. If we analyze the total axial dilatation of the columns as function of the intensity of the axial force and the time of fire exposure, it can be noticed that for all four shapes of cross sections, at the beginning of the heating process, the positive dilatation caused by temperature are dominant. Then, the negative dilatations caused by the axial force decrease with tendency to become positive, which is the case for load coefficient less than 0.3. After time, the average temperature of the column's cross-section becomes higher, the mechanical characteristics of the steel and concrete are reduced, the negative dilatations are dominant again, and are significantly larger than the positive dilatations caused by temperature. As a result of all this, the columns fail in compression. The most sensitive is the cross-section with dimensions 50 or 60 centimeters due to the high average temperature, and the best behavior shows the cross-section with dimensions 30 or 30 centimeters. Finally, we will give general conclusions. In case of fire exposure from all four sides and action of axial compressive force, There is a significant difference in the behavior of the columns with same cross-section areas but different shapes of the cross-section. Due to the compactness of the cross-section, the column with dimensions 30 by 30 centimeters has the lowest average temperature, consequently the highest fire resistance. And it is not a case with the column 50 by 60 centimeters, because in this case the temperature easier penetrates deeper in the cross-section, the column reaches the highest average temperature and has the smallest fire resistance. These fire resistance curves indicate that the highest fire resistance achieves the column with lowest ratio of two sides of the cross-section. The reason for that is the lowest average temperature of the column's cross-section. Thank you for your attention.